Hello IB. We just want to go over what we did in class on 15E on the derivatives of exponential functions. So what we started off by looking at was these different exponential functions, and we thought what's happening to the gradient as we move along our x-axis. So here we have a small gradient and it's getting steeper and steeper. Same story here, a small gradient getting steeper and steeper. We also talked about that at no point would these gradients be zero. We don't get a minimum on the exponential graph or a maximum. So there's no horizontal, so the gradient will never equal zero. And so we decided that our graph would look very much like our original graph. It would be an exponential graph as well, with the horizontal asymptote here. So f dash x never equals zero. So it's an asymptote to the x-axis. And we also saw that at, say, this point, the gradient for the y equals 5 to the x was steeper than the y equals 2 to the x. So at this point, it's steeper than this one. But then over here, it gets lower. And so at some point, that's going to change where this now is not as steep as this one. Where that exactly changes, we haven't worked out at the moment, but there'd be some point where these two gradients would be the same, and then they switch over. Later we find out that these y-intercepts here are actually equivalent to the natural log of 2 and the natural log of 5. So for y equal 5 to the x, this is its derivative function, and the y-intercept is ln of 5. We'll come back to see why that's true in a short time. What we then did was, using Excel, we set up an x and a y value for y equals 2 to the x, and that's the blue line here that we've got plotted. So that's the natural curve that we're seeing. Then what we did was calculate an approximate derivative function. So the derivative we could take as a chord, and I've shown this in yellow, say the chord between 0 and 0.2, which are these two values, and then divide that by 0.2, and that would give us the gradient at the midpoint. So it's like doing an approximation. So we filled in all these cells and found the different gradients at these points as an approximate of the chord straddling the points. So it's not exact, but it's a rough idea. We then found out that if we take the ratio of the original function and the derivative, the approximate derivative, so if we do f dash x divided by f of x, we found in this case it always came out of 0.6937. So in other words, the ratio of this height of the derivative function over the whole height always came out the same amount. So we then said, well, that means this is equal to 0.6932, and it's a constant, it doesn't change. So we could say that the derivative function is always 0.6937 times the original function. And we made these general statements. If we've got some base to the power of x, the derivative is a constant times that base, and this k is, we'll come back to see that, it's actually the natural log of the base. So where did we find that out? It was over when we started looking at the exponential e function. So if you may have looked at this earlier, but if I have this graph here, and we've set up y equals e to the x, so that's this curve here, when I work out the derivative function, which is this one down the bottom, so this is our derivative function, we see that it's following the same pattern. That's what we saw before. But what we actually find if we look over here at the table of values is that it's exactly the same. So in other words, if our function is y equals e to the x, the derivative function is also y equals e to the x. So it just doesn't change no matter what x values we look at. So that's this statement here, that f of x equal e to the x, then the derivative function f dash x is also e to the x. So we then talked about the chain rule. So if our exponential function has a little function in the top, so we've got like an outside function and an inside function, and to differentiate that, we follow the same chain rule. So y dash would be e to the f of x, so the outside function stays exactly the same when the base is e, times the derivative of the little function that's inside our exponential. So we get f dash x times e to the f of x. So we did some examples of this and went, what if we've got e to the 2x minus 3? Then our derivative function is going to be the same function when we think about the outside function times the derivative of this inside function, which was 2x minus 3. Derivative is just 2. So this becomes 2 e to the 2x minus 3. So note that that's multiplied together. This exponent up here only belongs to the e, not to the 2. We did another one. If we've got e to the 3x squared, then the derivative function f dash x is going to be e to the 3x squared. Leave it the same. Now differentiate this part to give us 6x. So let's go back to where we started with with f, the function equal to 2x. So remember, if we go back to our logs, if we have 2, then we can write that as some power of e. Remember, e is 2.718, etc. So there's some power that we can use that will give us 2. So using our log rules, so p is equal to ln of 2. So in other words, I can write 2 as e to the power of ln of 2. And if you do that in your calculator, if you put that in your calculator, you'll get approximately 2, allowing for some rounding. So that means our original function here, 2 to the x, we could write as e to the ln of 2 to the power of x. So these two functions are the same. We put the x in front of the ln, 2, just so that you don't get confused to think it's ln of 2x. So ln of 2 is just a number. It's like the coefficient of x. So any base we can rewrite as e to the x ln of a. Okay, so let's now start differentiating. Now we know that our rules for differentiating exponential functions. So if we differentiate this, we differentiate the outside, it stays exactly the same, e to the x ln of 2. Now we differentiate the inside. This is just a coefficient, it's just a number for x, so the derivative is ln of 2. So that means, let's put our ln of 2 at the front, ln of 2 e to the x ln of 2. So now we know that the derivative has an ln of 2 at the beginning. We can now swap this back for our 2 to the x. So if f of x is 2 to the x, we come down to the derivative function is ln of 2 times 2 to the x. And when we put ln of 2 in our calculator, we come out with 0.6937, which is the number that we came up here. So this number here is ln of 2. So that's where that number's coming from. It has a significance. We see that this is the value we actually get when x is 0. When x is 0, the derivative at that point is 0.6937. It is ln of 2. So let's see why that is. Next page. So if we put, there's our derivative function. So imagine if I put a 0 in here, then that's a 0. 2 to the 0 is 1. So it comes out as ln of 2. So if we go back to where we were, we saw that this value at 0 for our derivative function was 0.6937, which is ln of 2. And that takes us right back to our first page when we were doing that quick sketch, and we said at this point the derivative function is ln of 2. Now we know y. So that y-intercept is ln of 2. And if we look at the other pink function, the 5 to the x, then the y-intercept is also ln of 5. It's what the log, the natural log of whatever the base is. If we had a plot of this one, then the y-intercept would have been the natural log of 1.2. All right, so when we come back to here, it's basically the same idea, that if we differentiate this, then it's like having 1, which is ln of e, as that coefficient. All right, so let's see what we've come down here. Please do stop this and make notes and listen to it again, because there's some quite big ideas here that we're going through. So, e to the x, when we differentiate, we just know comes to e to the x, but we could also think of that as times the natural log of e, which is 1. If I've got 7 to the x, then the derivative function is ln of 7, 7 to the x. We then came down to, if we had just making a general comment here, if our function is f of x equal to b to the x, remember we got our k value from the derivative over the original function, and we can substitute in the 0. This is not quite right because I've mixed up numbers and variables here. Our derivative function was the natural log of b times b to the x divided by b to the x. That's what this expression would be. So if we want to find it at the point where x is 0, our original function becomes b to the 0. The derivative function at 0 becomes ln of b times b to the 0. That's equal to 1. This is equal to 1. So now we see that the ones are just 1, and we're left with the natural log of b. So in other words, that ratio, when x is 0, is equal to the natural log of b. So we can use this sort of relationship when our base isn't equal to e, even though it works with e as well. So when you've got e to the x, you can just differentiate it and it's just the same. But if the base is not e, then you need to multiply it by the natural log of b. Alright, we then went through some examples. This is another one that's similar. If I've got the function equal to 5.3 to the x, the derivative is going to be 5.3 to the x, that stays the same, times the natural log of 5.3. If I had like a composite function, so we've got 5.3 to that 2x plus 1, then differentiating it. Alright, so let's just put this, copy it down here. So our derivative function, rub this little bit out. Beautiful. So our derivative function is going to be the natural log of 5.3 times 5.3 to the 2x plus 1. So that bit stays the same, times ln of 5.3. But using the chain rule, we now need to differentiate this part when that is 2. So we've got to multiply by 2 as well. So the 2 comes out the front, and we end up with that expression for the derivative function. Note, you could put the 2 in there to make 5.3 squared, so it's remembering all your log rules. Okay, so in 15e, question 1f, differentiating this. Remember, if you've got a constant, that becomes a 0. We've got minus 2, so just write your minus 2 down. Differentiate e to the minus x. It stays the same, times the differential of minus x is minus 1. So minus 2 times minus 1 is plus 2, e to the minus x. This one here should ring a bell with the product rule because we've got two functions being multiplied. So split them apart. Remember the same rule. this is your u, this is your v. So do them separately. X cubed becomes 3x squared. V becomes e to the minus x becomes minus 1 e to the minus x. Substitute those in for u dash v plus v u dash. What have we got? So u times v dash, and simplify. The last one here is, and we've talked about this in class, rewrite this so you can either set it up as a product rule or as a quotient rule. So doing it like this, then you can do the product rule by turning your square root of x into the x to the minus half because it's in the denominator. Otherwise, just do your u dash, v dash, and follow through as a quotient rule. So practice doing both in case you do need to do both. This also takes you through how to, once you've done this substitution, how to tidy it up and get it back what I call maths manners. So we need to make that common denominator here by multiplying by 2 root x on the numerator denominator. Then once you've got that common denominator, then you can put that together. So make sure you can just keep working with your fractions. So because this is a common denominator, that can now come down into the bottom, and we've got the numerator left up in the numerator. So if you're having trouble with the algebra, please come and speak with us so that we can help you with it. But anyway, hopefully this has cleared up some of the things that people missed from class. The only other comment we had was in the textbook, they've written this in one of the questions, x exp minus 2x. That basically means e to the minus 2x. So that's just a different way of writing it. Anyway, thanks for listening, and hope this makes sense for you all. Have a nice evening. Bye for now.